Hello, I am Dhirasai, student at Software College of IT and E-commerce. Welcome to this hands-on walkthrough of a full security assessment. We will analyze a compiled binary that implements a router management web service. The target is protected by a modern mitigation stack, full railroad annex, PI, a stack canary, and event CET. Yet we will change two vulnerabilities to achieve remote code execution. Along the way, we will use Ghidra for static analysis, GDB for dynamic debugging, and we will explain every step of the exploit code. So rather than wasting any time, let's begin. First, I am opening my terminal and I am going to the directory where my binary is located. So let's first see the access of the binary. MD5 some cw2, and we can see MD5 some access of this binary file. And now I will see SSA 256 some as of this binary, and you can see here. And we will use file command to see what kind of file it is, and it is ELF 64-bit dynamically linked and strip file. So we will start by loading the binary into Ghidra. After the initial auto analysis, we navigate to the symbol tree to look at the main entry point and the request and draw function. So let's begin. Okay, so I'm opening my Ghidra. It's taking time. So I'm opening my Ghidra. Just wait a few seconds. Here is symbol tree, you can see, and from filter I will go to main function, and after going to main function we can see the code of main function over here. This program starts a web server on port 8080 and that mimics like a router management server. In this program it has a function named request handler, and inside it there are numerous functions responsible for doing tasks, as you can see in this screenshot, you can see in this code. After that I will go to request handler function, check what's inside it. So I will type request handler over here, and in request handler we can see here the ping status handler builds a diagnostic log line describing how many packets were transmitted and received. Attacker inference data is passed directly as the format argument of a print family call rather than as a data argument. That is, the pattern is effectively as an print instead of the safe as an printf. Because of this, format tokens embedded in the attacker supplied field are interpreted by the C runtime rather than treated as literal text. This lets an unauthenticated adjacent attacker cause the process to print values directly from the stack or registers into the server diagnostic log, including a pointer into the program's own memory. Since PI randomizes the executable base address at every run, this leak is what makes the rest of the attack possible. It defeats ASLR PI without needing any memory corruption at all. And then after, I will move to handle API ping function. Handle API ping function, and you can see handle API ping function code over here. And after scrolling a little bit down, we find over here that this should have used $0 instead of 0% packet. Information disclosure of process memory addresses defeating ASLR/PI on its own. This is a medium severity information leak. Chained with the overflow below, it becomes critical. After that, we will go to parse IP and zone. Parse IP and zone function. Parse IP and zone function, and over here, parse IP and zone is called from handle API config post when the server processes or configuration update. The function copies the user supplied zone string into a fixed size stack buffer without validating that the input length fits the buffer. Especially if the submitted value contains more than 3 dot characters, the functions enter a copy loop that transfer up to 256 bytes into ctx.zone. The destination buffer is smaller than 256 bytes, so once the input exceeds the buffer's real size, the copy continues writing past its end, overwriting adjacent stack and contents, including further of the stack, the saved return address, and the stack canary. And you can see the decompiled code over here. After that, let's move to the part of the Ghidra. My terminals GDB. After finishing this Ghidra part, we will move to GDB part. My GDB wasn't working in terminal, so I have taken screenshots for that to verify. In this screenshot above, this vulnerable point where SNPRIM leaks the address of the variable visible in GDB, and the RCX register store it in a log buffer. And this next screenshot confirms that this behavior is in more detail. This confirms that the function is vulnerable. Using the leak address, the base address of the program can be calculated. During this execution, the leak value was 0x5b4deb94203, and the resulting program base address was, you can see over the screen. The calculation is shown below. The same calculation has also been implemented in the exploit code too. I will show you later. Then the program enters the executes its logging function, which is why the leak address is visible in the log output shown earlier. The next step is taking the libc address. Doing so requires constructing a ROP chain, which turns in requires control of ROP and knowledge of the stack canary. As noted earlier, because the program uses fork, the canary can be brute forced. The child process terminates whenever the canary guesses incorrect, while the parent process continues running, giving unlimited opportunities to brute force the canary and subsequently leak the libc address. The canary was brute forced from the child process. Since the program uses fork, the GDB command set follow fork mode child was used to follow the child process and observe the override with a breakpoint placed at parse IP and zone plus 217. You can see that this is from our payload, and this is the last instruction of that functions, and our ROP gadget was being executed to leak the address of the libc. And you can also see here, from here we are leaking the address of libc, which you can see on register RIS RSI or buffer, and use FDS4, which is the FD of the socket. Using the same approach applied to this program base address, the offset required the determined libc address was calculated. You can see over here. So after that, let's move to the exploit development part. Okay. For that I am opening my VS Code. Let's go. Let's trust the author. And for that, let's do it. The exploit chain proceeds in 4 stages, which I will explain right now. Stage 1, authentication. In authentication, you can see over here, the exploit authenticates using the admin credential that was recovered from router config.json. After that, functions. There are also functions in this code which are used to convert addresses to bytes and filter specific bytes and convert them so that the program can keep copying. After that, let's move to this section where this code is extracting the token from JSON response, and this ping request is issuing a ping request to the address to expose the address. After that, let's move down and I build this authenticated ping code because to reveal the this is an address to reveal the program address, and this is for sending ping request. After that, let's go to get api.logs. This is for fetching the log. This is for fetching the leak address from logs, and this extract JSON body is for filtering the program address from log and converting it. And base address equals to leak address minus this value is confirming the recovered program base address. Now next stage is stage 3, brute forcing the stack canary. For that I have written code over here. This code is trying to brute force the canary, and over here in body, this part, overflow is done in this place, and where the can offset false, there is our canary is. I'm scrolling down onto my next function over here, and this code, this condition confirms that filtering response to see the correct canary byte. And in stage 4 we have building and sending the ROP chain. Using the recovered pi base address and canary, the exploit builds and sends the ROP chain to override the saved return address. It first leaks a libc address to compute the libc base, then redirects execution to invoke exe VEAD to spawn a shell. Let's move to the line where canary equals to canary 07, creating the gadgets for leaking libc address. Then let's move to 222 line. Here we are creating the gadget for leaking libc address again. In body part we have this exploit that will this is the payload which will leak the libc address using ROP gadget. And after that, in config.request we have here post, which is going to hit the parse IP and zone functions as shown above, and this body contains this payload that I show you just right now. After that we are moving to this code, and this code is to bypass ALSR calculating the base address for libc. And you can see over there I commented time for shell. This means this code is all this exploit is this part of the exploit is written to spawn the shell in terminal. As you can see over here, this whole payload, this will execute eggs VAD syscall as eggs VE is blocked by the program using seccomp. And at last, in config request is sending request to vulnerable parse IP and zone function. So I'm gonna show you how this exploit will work in terminal and get a shell. For that, I'm seeing what files are in my this location, and we have this binary file cw2, and I have this exploit written over here solve.py. So I'm going to see what is inside docker file. So for that I am using cat docker file, and here is given command to build docker. So at first I'm going to build docker. After that I am going to run my docker. Once the docker gets built, let's just have patience and wait. It's building my docker. I will wait few seconds whether it's worked or not. What is this happening as कत्रो टाइम लाग्यो हौ डकर यार. Oh, my Docker is built successfully. Now I'm going to run the Docker. And as you can see, my Docker ran successfully. For that, I'm going to confirm by using Docker PS whether it's running or not. As you can see, the cw2 is running properly. And now I'm gonna execute the exploit by using Python 3. Python 3 soft.py. Yes, this code was written in Python. After that, I'm going to enter, and you can see over here, boom, we got our sale, and we successfully bypass our router management service. So that was much for today. Thank you.